Now, to show that a function is not a linear transformation, it is enough to find an example for which one of the two conditions don't hold. For example, for this here, for f of x, if we were to plug in x plus y, right? So we plug in two vectors in R, two values in R, then we would get x plus y squared. However, this does not equal x squared plus y squared, which is what f of x plus f of y would equal, right? So f of x is x squared, f of y is y squared. If you add them, you do not get the same thing as plugging this in. Similarly, if you try to plug in f of x plus y, g of x plus, you plug in g plus y into g of x, according to this function, you would get x plus y plus 1, which does not equal x plus 1 plus y plus 1. X plus 1 here is g of x, and y plus 1 is g of y. So because g of x plus g of y does not equal g of x plus y, g of x is not a linear transformation. So these two are two types of problems that are not. So in your homework, that's what you have to do for 9, 13, and 15. Now, there are a couple of other types of problems in your homework. Problem like 23. Suppose that you have a transformation from R3 to R3, and it's given by, the transformation is given not by a function rule, but by what it does to elementary basis, to standard basis vectors. Well, what we need to do for this is we need to express the vector 2, -1, 0 in terms of the vector basis vectors 1, ijk, right? That's what these are. So you would say this is 2 times 1, 0, 0, minus 1 times 0, 1, 0. And there is nothing on the z there, so it would be 0 times this guy. But we don't need to mention that one. So now we're going to put this through the transformation. So because our transformation is a linear transformation, so we're told in these problems that t is a linear transformation, we are to assume that when we apply the transformation to this vector, it would be the same as applying the transformation to its linear combination. Now, because the linear transformation preserves addition, we can distribute the transformation to this. So we can say this is t of 2, 1, 2, 0, 0, there we go, plus t of -1 times 0, 1, 0. So this is because t is a linear transformation and it preserves addition. Next, because it preserves scalar multiplication, we can remove the constants and put them in front there. So we can say this is equal to 2 times t of 1, 0, 0, minus 1 times t of 0, 1, 0. Of course, we know what the image of this is because we're given it here. So this turns into 2 times 2, 4, -1, minus 1 times 0, 1, 0, which is 1, 3, -2. So we can go ahead with this computation, and we can say, well, this is 4, 8, -2, minus 1, 3, -2. So finally, final answer, 3, 5, 0. All right, then finally, if, let's say, your linear transformation is given in terms of some other basis, so 1, 1, 1, 0, -1, 2, 1, 0, 1 can be verified as a basis for R3. It's not the standard basis like before. This is ijk, that's the standard basis. But the idea is, first we want to express 0 to -1 as a linear combination. So we want to figure out what of the 3 basis vectors that we are given there. So if we can express 0 to -1 as a combination of 1, 1, 1, 0, -1, 2, 1, 0, 1, then if we can find numbers such as these, then we can apply the same rule as before and we can find the image of this linear transformation. So this is of course a system of equations like we've been used to finding, and now these vectors turn into columns like you remember, 1, 1, 1, 0, -1, 2, 1, 0, 1. We augment to them the 0 to -1 matrix, and then by the magic of Maple, or you can row reduce this by hand, actually row reduce this by hand because I couldn't access Maple. I got, and I verified that this works. So I got the identity here, and then 3/2, -1/2, and -3/2. What does that tell me? That means these numbers are the coefficients of the linear transformation. So that means I can express 0 to -1 as a linear combination of these vectors by putting 3/2 in front of 1, 1, 1, minus 1/2 times 0, -1, 2, minus 3/2 times 1, 0, 1. And next we put this through the linear transformation. So next I'm going to apply the linear transformation to it. And again, because this is a linear transformation, it preserves scalar multiplication and addition, so we can just distribute the t in this way. T over here, 3 over 2, t of 1, 0, 1. Of course, we know what these values are. We are given those values here, so we're going to use that. So we're going to say this is 3/2 times 2, 0, -1, minus 1/2 times -3, 2, -1, minus 3/2 times 1, 1, 0. This means 6/2. I distribute this so it's plus 3/2 minus 3/2. That would be my first coordinate. The second coordinate is 0 minus 1, and this would be minus 3/2. And the last coordinate would be -3/2 plus 1/2, and then nothing there. So finally, the answer here will be 3. This is times 2, so it's -5 over 2, and that's -1.